Hello, I'm Mr. Parker and this is question 4 on the OCR Mechanics 1 paper from January 2011. For more questions on this exam paper, click the link here or check in the video description. A block B of mass 0.8 kg and a particle P of mass 0.3 kg are connected by a light inextensible string inclined at 10 degrees to the horizontal. They are pulled across a horizontal surface with acceleration 0.2 meters per second squared by a horizontal force of 2 newtons applied to B. Most of that information is given in the diagram here. The force of 2 newtons, the light inextensible string at 10 degrees to the horizontal. I've added the mass of 0.8 kilograms here. We've also got the mass of P, which we're going to use in part 2, and we've also got an acceleration of 0.2 meters per second squared we'll add on later. In part 1 it says, given that the contact force between B and the surface is smooth, calculate the tension in the string. When we're working with two connected particles, we've got 3 choices about what we can do. We can either work with the system as a whole, we can work with particle B, or we can work with particle P. In this case, I'm going to begin by working with particle B, and that's because there'll only be one unknown. But if you didn't spot that, a good idea would be to set up a diagram and see how many unknowns you've got when you're working with each particle. Before I add any forces to the diagram, I'm just going to add on another angle up here. If I know that this angle between P and the horizontal is 10 degrees, and I draw another horizontal line here, using alternate angles, I can say that this angle up here is also going to be 10 degrees. Looking at the forces on the diagram, I've got 2 newtons pulling to the left. I've got a tension force pulling down at 10 degrees to the horizontal. And we've also got an acceleration to the left of 0.2 meters per second squared. There are other forces acting over here on P, but because I'm just going to work with block B, I can ignore them for the time being. So resolving in a horizontal direction, we'll take left to be positive. We've got 2 newtons minus a component of this T. As the direction we're going in includes the angle here, it's going to be minus T cos 10 degrees. And that's going to equal mass times acceleration, so 0.8 times 0.2. Let's rearrange to isolate T cos 10, adding T cos 10 to both sides and then subtracting by 0.8 times 0.2 gives us T cos 10 equals 2 minus 0.8 times 0.2. We'll simplify the right hand side. 0.8 times 0.2 is 0.16. Subtracting that from 2 gives us 1.84. So we get T equals 1.84 divided by cos 10. And that gives us 1.87 if we round to 3 significant figures. However, it's likely in a connected particles question that I'm going to need to use the tension later in the question, so I'm just going to store that in my calculator. In part 2, we need to calculate the coefficient of friction between P and the surface. This time, we're just going to consider the forces acting on particle P. And we'll start by putting the forces onto our diagram. The mass of P is 0.3 kilograms, so we've got 0.3 g for the weight. We've got a normal contact force, which we'll call R. We've got a tension pulling to the left at 10 degrees to the horizontal. And we've got a frictional force pulling to the right, which we'll call F lim. Remember that T is not an unknown. We calculated that earlier in the question. We've got that stored in our calculator. We've also still got an acceleration of 0.2 meters per second squared. So the forces on P vertically taking upwards to be positive, we're going to get R. We're going to have a component of T going upwards. Remember in the last part horizontally we got T cos 10. So this time it's going to be T sin 10 because it doesn't include the angle. R and T are both in the same direction, so they should have the same sign. And in the other direction we've got the weight of 0.3 g. It's not accelerating vertically, so the right hand side will be 0. And if we rearrange to get R, we get R equals 0.3 g minus T sin 10. But at this point we can use our value for T, so we get 1.86 multiplied by sin 10. If we use our calculator to work that out, we get 2.61 and so on. As we're not asked to find the value of R, there's no point in rounding that to 3 significant figures, but as we may use it later, we'll store this value in our calculator too. We'll store this one as B. When you use your calculator to store values in the exam, make sure you label which one's which so you don't get muddled up later on. Next we're going to resolve in a horizontal direction. We'll take left to be positive because that's the direction of the acceleration. We've got a component of the tension which will be T cos 10. and in the other direction we've got limiting friction. On the right hand side we've got mass times acceleration. Remember, this time the mass is 0.3, multiply that by the acceleration 0.2. Rearranging to get Flim on its own, we add Flim to both sides and then we subtract 0.3 times 0.2. So we're going to get t cos 10. Remember, the value of t is 1.86, so we can substitute that in. 0.3 times 0.2 is 0.06, and we're going to subtract that from both sides, so that will be negative. Remember, we've stored the value of t in our calculator as a, so we get a cos 10 minus 0.06, and that gives us 1.78 for Flim. Finally, using the fact that limiting friction is equal to the coefficient of friction times the normal contact force, rearranging we get mu equals Flim, which is 1.78, divided by R, which is 2.61. I've got the 1.78 in my calculator. R is stored as B, so I can do this divided by B. And that gives me 0.681 if I round to 3 significant figures.